I will check the audio for a second before I get anything else. La la la. All right, good. We begin with a word of prayer once I get up here. All right. So, Heavenly Father, we thank you for this day again. I thank you for this class, and just pray that you be glorified in what we do, and that we just all understand a little bit more about linear algebra together, Lord. In your name I pray, Lord Jesus. Amen. All right, so today on the schedule, I put coordinates, non-standard coordinates in Euclidean space as the topic, and so we'll try to hit on that a bit. I printed out a couple of examples, and then I never actually went to the printer, so that didn't work. I guess I'm back to the laptop here. So this is in my chapter 5, but it's kind of I'm adding something here, guys, okay? But coordinates in Rn with respect to non-standard basis. All right. I suppose before I even talk about how the non-standard basis works, it probably would be good for me just to take a second to talk about the standard basis, right? So let me do that. So, I mean, we've been using these. So if we have x is an element of Rn, then we know the drill. X is equal to x1, x2, xn, which I can rewrite as like x1 times 1, 0, 0, plus x2 times 0, 1, 0, and then so forth and so on. Xn times 0 all the way out to 1. Now these vectors that I just wrote are the standard basis, right? This is E1, this is E2, this is E3, right? And you notice that I could rewrite this whole equation like, I could rewrite it like this. I could say, well, that's really just E1, E2, En times the vector x1, x2, xn, right? So here, this matrix I just formed right here, this is the so-called basis matrix. Basis matrix for standard basis right, is what? What is that matrix, by the way? What happens if we put E1 in the first column and E2 in the second column? And it's the identity matrix, right? So it's the identity matrix. So this whole equation I'm writing here, it's kind of silly, right? Because I'm really just saying x is equal to Ix if you want to rewrite what I just wrote there, all right? Now, so let's talk about non-standard basis. So let's let beta equal to, say, v1, v2, vn, all right? Let this be a basis. And what would that mean? So that means two things, right? What are the two things that we have here, if that is indeed a basis for Rn? You guys remember? That means two things, right? Number one, the span of beta is what? I know it's early, but someone knows. What's the span of beta have to be if it's a basis for Rn? It has to be Rn, right? First of all, you have to be able to build any vector in Rn by linear combination of the bases. And number two, beta has to be what? Linearly independent, right? So we have a linearly independent set of vectors. So if that's the case, then here's the definition. If x is an element of Rn, all right, and let's say x bar, well, I don't know, I'm trying to decide on the notation here. I'm going to use C's for the moment. C1, C2, Cn are real numbers such that x is equal to C1 V1 plus C2 V2 plus plus Cn Vn, all right, then the coordinate vector of x with respect to the beta basis is equal to C1, C2, Cn. And, you know, do remember our convention here. This is a short notation for a column vector, right? I got this sneaky hidden column vector notation. So the coordinate vector is itself a coordinate, a column vector. Right. Other notation, we also say that phi sub beta of x is equal to x beta. So that's it, folks. Though that's the definition here. Now here I'm also this part above here is part of the definition. We have to know that beta is a basis. If beta is not a basis, I have no business, you know, saying this. But there it is. All right. So can you guys tell me a simple condition that we could check to make sure something's a basis for Rn? Like what would be something we could do? How about this? I'm going to say V1 is like 1, 3, and V2 is 0, 4 for the sake of discussion. Does that form a basis for R2? My basis matrix would be what? It would be 1, 3, 0, 4. Are the columns of this matrix linearly independent? What's a super lazy, easy way we can check now? Determinant. Yeah, just take the determinant. If the determinant's non-zero, it's an invertible matrix. Therefore, by the theory we've discussed, it must be that the columns are linearly independent. And because there's two of them, the theory also says it must be a spanning set. If we have two linearly independent vectors, they provide a basis for R2. So note, the determinant of beta is 4, which of course is not equal to 0, right? All right, so if I have the vector x, which is, let's say, a comma b, let's think about the particular point, a comma b. Can we find what the beta coordinates are of that? All right? So what's x sub beta if x is equal to ab? How do we figure that out? So we're trying to solve what? We're trying to solve like c1 v1 plus c2 v2 equal to that, right? How else can we look at that? Well, let's think about this. We can think about this as a matrix problem, right? We can think about this as the matrix v1, v2 times c1, c2, right? So what does that tell me? That tells me that like c1, c2 should be equal to what here? 1, 0, 3, 4 inverse times the, you know, x vector, which here was AB. Can you guys write down the inverse? I think we can do. It's a 2 by 2, right? So remember the formula? Here we go. It's what? 1 over 4, right? Because that's the determinant. Flip the diagonals. Minus is on the off diagonals. Minus 0, 0. And so if I can do that multiplication, looks like we've got 4a over 4, which is 4a. And minus, then 1/4 of minus 3a plus b. So let me just continue this example. So here we go. We just figured out that the beta coordinates of x are, what were they? They were 4a, comma, 1/4 of minus 3a plus b. All right. Yep. No, I said it was just a, and then I wrote 4a. Thank you. Yes. Maybe I should fix that too. All right. No, I want to be real concrete with you guys here for a second. Let's actually try to work out what this means for a specific vector, rather than I found the formula here, you guys, for like an arbitrary vector AB. But let's see if we can specialize this a bit here to like a specific vector, and I'll even graph it. This is probably a bad idea, but let me think about this for a second here. I want everything to work out whole number, so all right. So let's see here. Maybe I'll make x equal to, just for illustrative purposes, 4, comma, I don't know. Six. Oh, that's too obvious. 4 comma, we'll do 4 comma 0. At least that's easy to graph, right? All right, so where's 4, 0? That's like here, right? This is x. So what are the coordinates of 4, 0 according to this formula?
4,
I heard a 4, -3. Do you guys agree?
4 negative.
4, -3. All right. I think that's right. If we plug 4 up in here, we get a -12. Well, anyway, the 4's cancel. We get a -3. The b is 0, right? All right, what does this mean? By definition, let's talk about this. What this means here, right, means that 4, 0 is equal to 4 times v1, right, minus 3 times v2. And for our current example, that's 4 times, what was my v1? 1, 3, right? Minus 3 times my v2, which was 0, 4, right? Okay, so let's see if I can graph that. 4 times 1, 3. So 1, 3, I probably have chose too large a scale. We'll just deal with it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh well. Poor planning on my part, I think. So 1, 3 is what? Over 1 up 3. So like this is 1, 3, right? This is 1, 3, but we're doing 4 of those, right? So I do another one, another one, another one. So this is 4v1, roughly speaking, right? And then, let me do it in blue. Well, it's already in black, so I'll leave it in black. So that's this piece. And then minus 3, 0, 4. So that's like one of these, two of these. Not the scale, guys. It's the best I can do, okay? So this is minus 3 times V2, right? And as you can see, that gives me back down here, which of course is just my x. Yeah. So this is the idea of coordinates, is like we can build a point either using Cartesian coordinates, which everybody understands, right? We go so much to the left and so much up or down. That's what x1 comma x2 means, right? But if we have, let's see here. So let me introduce yet another notation, if you guys don't mind. So let us suppose that we looked at the coordinates of x and y with respect to the beta coordinate system, and let's call those like x bar, y bar for new coordinates labels. So if you did that, what's x bar equal to here? What's y bar equal to? So I used a and b as a starting point, but basically a is equal to x, b is equal to y, right? So x bar is equal to x, and y bar is equal to 1/4, minus 3x plus y. So these are, new coordinates x bar and y bar that we could graph those, right? So here is y, here is x. This one's kind of weird because when I draw the new, I'll draw the new axes in red. First of all, the x bar axis is the same as the x axis, right? I think. I could be wrong about that, actually. My bad. Oh yeah, my bad. How do we decide where the axes are for another coordinate system? It's a little bit sneaky. Think about this. What are the equations for the x and the y coordinate axes in terms of Cartesian coordinates? You ever think about this? Maybe not, right? What's the equation for the y-axis? It's what? It's x equals to 0, right? What's the equation for the, I'll put it up here. What's the equation for the x-axis? Yeah, y equals 0. So if I want to understand where the new axes are, right, with respect to the non-standard coordinate system, I should look at what? What equation should I look at? I should look at x bar equals to 0 and y bar equals to 0 to understand where those are, So x bar equals to 0, which of course is just x equals to 0, and y bar equals to 0, which is in fact, in this case, minus 3x plus y over 4. So it looks like that gives me y is equal to 3x. This describes the y bar axis. So I guess I was actually right. The x-axis is the same as x bar, because it's still, oh, I'm an idiot. What am I? Good grief, people. Me, not you, obviously. This is why I shouldn't teach it this time. So the x bar is what? This is the equation for the y bar axis, right? That we just got done saying. So what this all means is that the y bar axis and the y bar and the y axis are the same. All right, so this is the y bar axis actually, because this is x bar equals to 0 is this. Now y bar equals to 0, which gives me the x bar axis, is actually y equals to 3x, which is something like, well, obviously not, I mean, slope 3 is pretty steep, right? So, oops. So there's your x bar. So obviously, these are no longer they're not ortholinear coordinates, right? Like, well, how about this? What's the distance from the origin? What's the distance from the origin for x? What's the square root of x1 squared? Well, let me see here. I gotta choose a notation. Well, let's just look at our example. So notice that if we use Cartesian coordinates, the magnitude of x was what? Like the length of x is the square root of 4 squared plus 0 squared, right? Which is what? 4, right? The length of that x vector was 4. If we were to assume wrongly that we could still calculate the distance from the origin in terms of the new coordinate system by the square root of the sum of the squares, we would be dreadfully wrong, right? This is not equal to the square root of 4 squared plus minus 3 squared, right? That just happens to be 5, right? 5 is not equal to 4. So these coordinate systems, if we use non-standard basis, we lose things, like we can no longer calculate the distance between points with the square root of the difference of the squares in these non-standard coordinates, right? Because these new axes, they don't respect things like, well, the x and the y coordinate axis being perpendicular, right? That's the basis for which we have the Pythagorean theorem and other things. So, all right, so anyway, enough of this example. Let us move on here. Let me recap. So general, here's the calculation. To find the coordinate vector with respect to x beta is we can write x is equal to, let's say, C1v1 plus C2v2 plus CnVn, but that we can rewrite as the matrix v1, v2, vn times the coordinate vector c1, c2, cn, all right? And specifically, that's the beta coordinate matrix times the beta coordinate vector. So in short, if you want to calculate the coordinates of a point with respect to a non-standard matrix, what do we need to know? I just did it in my example 1, but my point to you is that this is generally the problem of finding coordinates with respect to a non-standard basis. What do we need to do? We need to be able to do what? We need to be able to solve for x beta, right? How do you do that? So let me underline the problem here. We have matrix beta times the coordinate vector we're trying to find equals to x. How do I solve for this? You guys tell me? Very good. Right. We simply multiply by the inverse beta matrix. So inverse x beta inverse times the beta matrix times x beta is equal to the beta inverse matrix times x. This, of course, is the identity matrix. Therefore, we get that the beta coordinates are equal to the inverse to the beta matrix times x. And that is how you do it. To find the non-standard coordinates of x, we simply have to multiply by the inverse of the basis matrix. That's it. Now, like, this notation is okay, but let me introduce yet another notation. So like same song and dance here, same idea, better notation. I'll put a question mark on that. You can be the judge. But a lot of times I like to use a notation, and this is of course common in like science or engineering as well, to use a notation for the basis which is echoed by the coordinates that correspond to the basis. So one way we can do that is maybe my basis, I put a bar on it, beta bar, and that's V1 bar, V2 bar, Vn bar, all right? And I'll say with coordinates, x bar 1, x bar 2. What do I mean by that? What I mean by that is that if we pick any point x, we can write it as x1 bar, v1 bar. Like that, right? Which, to loop us back through the same calculation again, that can be rewritten as v1 bar, v2 bar, vn bar times the x1 bar, x2 bar, xn bar, right? Which, by the way, is the beta bar matrix times the x beta bar coordinates. Which perhaps we could just write as, I suppose we could write that as x bar if you wanted. You know, I think that wouldn't be wrong. Do you guys see that? I don't always do that, but it occurs to me I could. And if you did this, what's the formula then? We see that, the beta bar coordinates is just what? It's the beta bar inverse matrix times the original vector x. Do you guys remember we talked about a special kind of coordinate system? Well, not coordinate. We talked about a special kind of matrix like last week, a so-called orthogonal matrix. Remember how that worked? It was what? It had an orthogonal matrix was one which satisfied what? Do you guys remember? Let me jog your memory here. We had R transpose times R equals to the identity, right? So R inverse is equal to what? R transpose, right? So if we had a so-called orthonormal basis, right? If we had a set of vectors which were actually pairwise perpendicular in all length 1, if we look at the basis matrix for that, the inverse is much easier to calculate. It's just the transpose. Let me illustrate what I'm saying with an example. Let's see here. Let's see here. So consider R3, and let's look at the vectors 1, 1, 1 divided by the square root of 3. So 1 over the square root of 3 times 1, 1, 1. And then V2, how about this? 1 over the square root of 2 times, hold on a second. I guess I got to do 2 minus 1, maybe. Yeah. What's the length of 2 minus 1, 1? 4, 2 squared is 4. 4 plus 1 is 5. 5 plus 1 is, so square root is 6. Can you guys tell me a third vector which is perpendicular to both of these? Like, tell me a vector which dot products with both this and this to give 0. the thing I haven't written down. Let me think through it. 0. Minus 3. What, 3? No. Yeah, minus 3 maybe. 0? No, that doesn't work. Sorry, guys. You guys tell me. Why should I do everything here? Get to work. What vector can I put here which is perpendicular to both v1 and v2? Zero. See, that one works. That one makes this one go away, but then it's troublesome up here. Wait a minute, or is it? Oh no. All right, sweet. Thank you. Good job. Guessing for the win, right? What's a way to not guess and to find a third vector perpendicular to the first two? You're in calculus 3, right? I thought you said you're calculus 3. Different calculus?
It's like an intro one.
An intro one. Ah, rats. In calculus 3, we learned about this thing called the cross product. If we take two vectors and we take their cross product, it gives us a third vector which is perpendicular to the first two, you know? But anyway, guessing is also legitimate. So cool. All right, so these, I believe, are all length 1 and they're perpendicular. So this makes beta v1, v2, v3 a so-called orthonormal basis. And so in particular, that means vi dot vj is equal to Kronecker delta ij. It's 1 if I is equal to j. It's 0 if I is not equal to j. All right. So let me call this beta bar because I want to stick with my notational scheme that I just introduced, and I like this. So what are the formulas for x bar 1, x bar 2, y bar 1 in terms of xy, x1, y1, in terms of x1, x2, and x3? Or maybe we can use x, y, z. So let's calculate I'll make up my mind eventually, guys, here. Let's calculate the beta bar coordinates of x, y, z. All right? So I'm saying that is the beta bar matrix inverse times the vector x, y, z. All right? And I'm telling you that, in fact, since this is an orthonormal basis, we can calculate it like this. It's beta bar transpose times x, y, z, because this is a nice basis. Now, you can try me. Let's try it out. Let's make sure I'm not, selling you a bill of goods here. What is beta bar matrix equal to? You got yourself 1 over root 3, 1 over root 3, 1 over root 3 for column 1, 2 over root 6, minus 1 over root 6, minus 1 over root 6 for your column 2, and then we've got 0, 1 over root 2, minus 1 over root 2, right? What's the transpose of that? We just make the first column the first row. We make the second column the second row. And then we make the third column the third row. When I stand close to the board like this, I hear Dr. Schweitzer teaching. It's very hard to not be distracted and try to figure out what he's saying. But anyway, so that's the transpose. If we multiply these two matrices, are they inverses? I sure hope so. So this vector times that, what do I get? I get 1/3 plus 4/6. 1/3 plus 4/6, also known as 1/3 plus 2/3. Hey, that's 1. Yay. If I take this and I take the dot product with that, I get, 1/3. Oh man. I get 1 over the square root of 8. No, I get 2 over the square root of 18 minus. Oh, I can't do math. My brain. I think I get 1/9 minus sorry, I can't see things. Oh, no. I thought for a second there I had tricked myself that these weren't actually orthonormal. I think they are, though.
Are you multiplying the
I was trying to, yeah, I'm trying to multiply them in my head. I was trying, which is probably a bad idea. I was trying to multiply this by that for like the 1/2 component. So that gives me 1/3 minus 2/6. Oh, that's 0. It's fine. It's fine. So you can check. You can check. Maybe I shouldn't try to check, but you can check that beta transpose times beta indeed is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. All right? This is obviously very nice because calculating the inverse of a 3x3 matrix, right, is pretty tough. So this is, 1 over root 3, 1 over root 3, 1 over root 3, 2 over root 6, minus 1 over root 6, and minus 1 over root 6, and 0, 1 over root 2, 1 over root 2 times what? Times x, y, z. And that gives us, I'm going to write it this way because it's easier to read, x plus y plus z divided by the square root of 3, comma, 2x minus y minus z divided by the square root of 6, comma, y plus z over the square root of 2. That, my friends, is the x bar, y bar, z bar coordinate system. If you were to actually be able to graph this carefully, what you'd find out, and this is just a pneumatic, like a mnemonic picture, all right? It's like this is x, y, z, right? The x bar, y bar, z bar axes, if you could graph them, they're simply obtained from the original axes by a simple rotation. In this case, like the new coordinates are like this, something. I'm not sure exactly where they are. This is just like, schematic, but let me put some scare quotes around this picture. But fun fact, guys. What do you think it's going to be if we calculate x bar squared plus y bar squared plus z bar squared? Right? Which would mean what? X plus y plus z over root 3 squared plus 2x minus y minus z over the square root of 6 squared plus y plus z over the square root of 2 squared. What would that work out to? Not 1. Good guess. Somebody guessed 0. Also wrong. It was a trap. 2 is also wrong. Nice try, though. It probably depends on x, y, and z, right? If this picture is right, if these are still perpendicular to one another, if you think about it intuitively, it must mean that the distance from the origin in the x bar, y bar, z bar system is the same as the distance from the origin in the x, y, z system. So for this kind of coordinate system, unlike my example 1, where the distance was spoiled by the non-standard coordinate system, here you would actually, and you can do the algebra. Do the algebra and you'll work it out and you'll get x squared plus y squared plus z squared. So orthonormal coordinate systems are very special. They still preserve the same notion of distance. All right? Non-standard coordinate systems, not so much. How do we calculate non-standard coordinates? I showed you today. It's very simple. We write down the basis matrix, we find the inverse of it, right? Here, let me show you one that's not as simple. I'll let you guys work it out while I run and print it. Oh. Actually, let me just show you. Let me just use the projector. That'd be smarter. I'm so annoyed. I actually prepared these before class, and then I was talking to Dr. Schmidt for like 3 seconds. And in that 3 seconds, or the 3 seconds, I forgot to hit the print button. But I found an amazing matrix. All right, I found an amazing matrix for purposes of this discussion, which I have failed to properly implement in class. Come on. All right, so I have 2 lightning round examples for us at the end of class. The one is kind of already contained in that right there, okay? So, what does this calculation mean, guys? I'm calculating the inverse. So, let me write it down here. So if we had beta equal to 1 minus 1, 2, 2, 0, 1, 3, minus 1, 7, right? The beta inverse matrix works out to, after some calculation, Can you guys read off that? Oh, I can see it. 1/8, right? 5/8, minus 1/8, minus 11/8, 1/8, 3/8, minus 1/4, minus 1/4, 1/4, right? So if I was to calculate the, let me call this the beta bar for this, I like the bar notation. So if I was to calculate the bar coordinates of x, y, z, what would I get? I would get, I have to multiply this by x, y, z, so I get, 1/8 x minus 11/8 y minus 1/4 z, right? I get 5/8 x minus, or plus 1/8 y minus 1/4 z. I get minus 1/8 x plus 3/8 y plus 1/4 z. That is what I just did there was beta inverse times x, y, z, right? That's how I calculated this. But there you go. That's the x bar, y bar, z bar coordinates with respect to that non-standard basis. Now this is not the one that was amazing. Check this out, guys. If I can find it. This just happened. This is my other example that I was going to do today, but I neglected to. Maybe I'll come back to this next class. I don't know. I'm going to save it. We're probably out of time here at the moment, but check out this. So this would be these. So suppose I had the basis for R4. This vector, this vector, this vector, this vector, right? First of all, they actually are linearly independent. If you calculate the row reduction of this to find the inverse of this 4x4. After some, aw man, you stupid umbilicus. Do your job. There we go. All right, so check this out. As you saw in my previous example, almost always when we invert a matrix, we get fractions, right? Check this out, though. It's cut it at the page, but the inverse to this 4x4 is integers. That may not be impressive to you, but to me, when I'm trying to make a test or something, I oftentimes spend a fair amount of time just tinkering with something to try to get the determinant to work out nice so there's no fractions in the inverse. Because fractions kill you guys, right? And me. This, though, is a 4x4 matrix that the inverse actually is no fractions, which is kind of cool. So if I was to find like the coordinates of A, B, C, D, I would just multiply by this matrix times A, B, C, D. That would give me the non-standard coordinates with respect to the basis that corresponds to the 4 vectors I started with. But anyway, so next time, guys, we'll start talking about linear transformations. And actually, this coordinate map is the first and perhaps most important example of a linear transformation. I'll explain more why that is next time. So have a good weekend, guys.